everybody, we're going to be going over Unit 2's FRQ for practice today. This is going to be the 2013 exam, question number 6. Now, this exam question was written before the redesign happened, and so you'll notice that this entire question here is all about intermolecular forces and Lewis structures. I can tell you that that's probably not going to be the case anymore, so you're going to see a much more integrated FRQ, where you'll have maybe one chunk being kinetics, one chunk being intermolecular forces, and another chunk being gas laws. But I still think it's a really good FRQ, and so I think we're gonna, just go over it and do it anyways. So if we start off, you're given a table where you have two compounds. They have the same empirical formula, but they have different properties. So the top one, compound 1, is slightly soluble in water. Compound number 2 is very soluble in water. So instantly I'm thinking, hey, they might be asking me a question about polar and nonpolar here. And then I've got two boiling point differences that are happening. So if I take a look, it tells me they have all that stuff. Oop, I did that already. So A, it says the skeletal structure for one of the two compounds shown below in box X. It says complete the Lewis electron dot diagram of the molecule in box X. Include any lone non-bonding pairs of electrons. I know that your first inclination in these situations is to figure out the Lewis structure by just connecting things based on your habits, but I would always recommend figuring out how many electrons need to be in these particular Lewis structures. So my formula is C2H6O. So figure out how many valence electrons are in there, because if you don't do this, you could potentially be causing some issues. So carbon each has 4, and there are 2 of them, so that's 8 electrons. There's 6 from the hydrogen, and there's 6 from the oxygen. So I've got 6 plus 6 is 12, and 8 means I got to put 20 electrons in my picture. If I go through and I connect everything with a straight line to start off with, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 lines drawn in, 2 electrons taken away for each of them. It means I'm taking 16 electrons out of the pot, because I already have in my picture, which means that I have 4 electrons left. When I go through and I look at my Lewis structures here, check everything out, everything is good except for the oxygen, and it needs 4 electrons, and I've got 4 electrons, so everything is right in the world. And there's my Lewis structure. This group here on the end is called an alcohol group, just in case you guys were curious. This is ethanol. This is actually the stuff that you can drink. All right, in box Y above, draw the complete Lewis electron dot diagram for the other compound, which is a structural isomer. So a structural isomer means that it is the same chemical formula, but it has a different structure to it. And so what I am going to do is I am going to be drawing something that's similar to this in the number of elements that it has, but different in its structure. So there is, I think, the right one. And in the correct Lewis structure, I would have the O in the middle. So I'm just going to kind of slide the O from the end to the carbon here and switch them around. However, well, this is the correct Lewis structure. Now, I know it's correct just from experience taking organic chemistry, but that doesn't mean that this is the only correct answer. You could draw something like this. I'm going to kind of draw it off to the side here. Sorry for the terrible picture. You could literally just switch the carbon and the hydrogen in this Lewis structure and have another one. As long as your Lewis structure follows the correct rules and it follows the rules of the Lewis structure, so everything has 8 around it, you don't have more electrons than you're supposed to, you are going to get that point. So even if yours doesn't correctly match 100%, the AP graders are trained to accept a ton of different answers. I think that I've seen it one time where there were 7 possible correct Lewis structures that you could draw, so they're trained to look for everything. Okay, for part B, it says on the basis of complete Lewis electron dot diagrams you drew in part A, and the information in the data table above, Identify which compound, 1 or 2, has the structure represented by box X. Justify your answer in terms of the intermolecular forces. So they're already cueing me towards thinking about the intermolecular forces. And we all know that intermolecular forces have a role to play when we are talking about our Lewis structures. Now, depending on how you draw your Lewis structure, you are going to maybe have different answers. So if I am talking about this Lewis structure in box Y versus box X, I could have very different answers than if I had this Lewis structure. So I'm going to walk you through both of them, and then we'll kind of talk about them. If you look here, the compound number 2 has the higher boiling point, and that means that it's more difficult to take that compound out of its liquid phase. Intermolecular forces that are likely going to cause this are going to be things like hydrogen bonding. So what we want to do is we want to look for hydrogen bonding. If we look at box X for the original structure that they give us, hydrogen bonding is present in the Lewis structure in box X. And for my Lewis structure, with the O in the middle and no hydrogens attached to it, I would say that there is no hydrogen bonding in this structure. There's dipole to dipole. So what they're looking for is you to discuss both of them. It says justify your answer in terms of intermolecular forces in each compound. And in my mind, when I see that, it tells me I need to talk about both of them. So I would probably start by talking about compound in box X. I'd say the compound in box X is capable of hydrogen bonding and it has London dispersion forces and dipole to dipole interactions. Oops, excuse me, it's hard to write on the fly here. Okay, then I would talk about, and you see here I said the compound is capable of hydrogen bonding. I got to be specific, so I'd say the compound in box X. I would follow it up by saying the compound in box Y is capable, I'm spelling wrong, of dipole to dipole interactions and London dispersion forces. Okay, so I've met the criteria about talking about both of them. They're going to look for that to give you 1 point. The next thing you need to do is actually answer the question. So I'm going to say compound X is likely compound 1 because of its ability to hydrogen bond. And then I'll say something like hydrogen bonding is the strongest intermolecular force. So it's the strongest intermolecular force. And substances that are able to do it have higher boiling points than those that can't. Okay, so I would have something kind of like that going on in my explanation. I'm talking about the types of intermolecular forces and they explicitly tell me to do that. And then I talk about what's going on. So just be aware that there's kind of a lot of writing with this one. And intermolecular force questions typically have those, a bunch of them. Okay? All right. It's a lot of intermolecular forces with this question. So it says for the next one, it says use the information in the following table to answer parts C and D. And you say, my hand is tired and I'm already done with this. So in this case, I give you a box with 2 substances, 2 diagrams are ready, boiling points, vapor pressures. So when we look at these, again, things with the highest boiling point have the strongest intermolecular forces. So in my head, I'm already saying to myself, this compound, carbon tetrachloride, is going to be the one with the stronger intermolecular forces. So for C, it says dichloromethane has a greater solubility in water than carbon tetrachloride has. Account for this observation in terms of intermolecular forces between each of the solutes and water. So I've got my 2 Lewis strictures here, and I look at carbon tetrachloride, and I see that it has C to Cl, which tends to be polar, but I have 4 chlorines around that carbon, which means this shape is going to be tetrahedral, and because it's tetrahedral, it is nonpolar for carbon tetrachloride's polarity. When I look at dichloromethane, I have the asymmetry that we've talked about where some of the bonds are polar and some of them aren't. And so dichloromethane is going to be polar. So these are the things that I'm going to have to start talking about with the interaction. So what I'm going to say for question C, it's telling you to account for the observation in terms of intermolecular forces between the solutes and water. So what I would say is I would say dichloromethane is polar, which means that its dipole to dipole forces will be attracted to water. Okay, so you're talking about how the dipole to dipole forces from the compound make it want to stick to water. In the case of carbon tetrachloride, and you can be fancy with your words, or if you're in a hurry, you don't have to. So in the case of CCl4, the molecule is nonpolar, which means it's only London dispersion forces and water interacting with each other. And I'm going to make a little note maybe back up here. Then I'm going to talk about water, which is also polar. So back to the sentence. In the case of CCl4, the molecule is nonpolar, which means there are London dispersion forces interacting with the polar water. Okay, so I've talked about both of them. Then after I've talked about them, I will say because LDFs only do not interact strongly with water's dipole, the CCl4 will not dissolve well. Okay, so what I've talked about in here is I've talked about the intermolecular forces and how they attract with water. I think I should be good to go. Okay. For D then, it says in terms of intermolecular forces, explain why dichloromethane has a higher vapor pressure than carbon tetrachloride. So because CCl2H2 here has a higher vapor pressure, it means, a higher vapor pressure, it means that it's easier for those atoms and molecules to escape the surface. If you remember vapor pressure, this isn't what you have to put in your response. This is just a quick review. So if I have CCl2H2 here, vapor pressure is the pressure of how much vapor is at the top of the surface. So if we compare the two at a specific temperature, CCl2H2 and then CCl4. Since CCl4 has a smaller vapor pressure, it means that less of this liquid is able to turn into a vapor, which means that it has stronger intermolecular forces. So what this vapor pressure is telling me, and the melting point, I'm sorry, the boiling point, what it's telling me is that it's telling me that the intermolecular forces in CCl4 are stronger than they are in the CCl2H2. So they're weaker. Okay. So what I need to write in here is basically that discussion. So I would say, even though CCl2H2 is able, or maybe not able, has dipole IMFs, its higher vapor pressure means it has weaker intermolecular forces than CCl4. Which only has London dispersion forces. The larger size of CCl4 means it has more electrons, which strengthen London dispersion forces. Okay, so in this case, they're saying 2 points are earned, one for referencing the types of intermolecular forces in each of the two compounds, and then discussing the difference there. I can tell you that they aren't going to have a ton of these FRQs that are just writing upon writing upon writing. They kind of went away from those more in the new exams, so if it feels like you've been writing your arm off, you have, and they don't do that as much anymore. All right. Finally, to the end of this one, it says the complete Lewis electron dot structure of methanol, which is formaldehyde, is shown in the box below. Molecules of methanol can form hydrogen bonds with water. In the box below, draw a water molecule in a correct orientation to illustrate a hydrogen bond between a molecule of water and a molecule of methanol. Use a dashed line to represent the hydrogen bond. Now, we have specifically talked about how things that hydrogen bond need to have an O to H, an N to H, or an F to H. And that is if hydrogen bonding can occur in that substance with many of its own molecules. However, sometimes you end up in situations where you have polar bonds that are able to make a hydrogen bond with something else. And if you know your structures, and you really should have it written down, that C to H is a nonpolar bond. C to H is nonpolar. C to H in the other direction is nonpolar, but the C to O bond is polar. Now, carbon has an electronegativity, I believe, of a 2.5, and oxygen has a 3.5, which means that if I look at my polarity, carbon is going to have a partially positive charge, oxygen is going to be partially negative. Honestly, oxygen is partially negative in just about every bond except for one with fluorine. So if we want to talk about drawing a hydrogen bond with water and how it's going to interact, this is basically just like every other hydrogen bonding that you've shown. Remember that you draw it with dotted lines attracting the partial negative of the oxygen to the partial positive of the hydrogen. You do not want to draw an actual physical line because a physical line represents a full bond instead of an actual hydrogen bond. So hopefully this clears some stuff up. If you have any questions, let me know.